Okay, so it's great to see this classroom so full. I haven't seen it so full. And please introduce Shamgar Gurevich from Wisconsin, who will tell us about representation of S2Q. And after this talk, we'll immediately run to the other lecture room.
Yeah, Roger. Yes, you see.
After this talk, we'll immediately run to the other room to continue. Please.
Okay, thank you. Thank you for organizing this. So I want to think about this as this topic as part of harmonic analysis. In harmonic analysis, we take it's a function on the line, expand it as a sum of exponents, and study the function by studying the terms in the expansion. And important that every exponential has a frequency. And I would like to talk about generalization of this idea of order from many years ago. And I'll do it in the case of the group SL2FQ, which is in some sense the first non-trivial example where this appears, but you can also then compute everything really explicitly. So, why did it move? The lecture ends.
We call the guy. But you're in the Zoom, that's not, where is your presentation?
Yeah. Let me again.
I would go with somebody younger.
Sure. Okay, so I'll start with motivation. So you have a finite group. Suppose you have a representation of it on a finite dimensional complex vector space, this calligraphic age. You can take the trace of the various operators, and you coming from G, so you have rho G operator for every G. Take the trace, you get this character function, and sure explains that if you start with irreducible representation, no invariant subspace, and then you get this irreducible character, and they form an orthonormal basis for the space of class function invariant to conjugation on G. Second step is, want to think about it as a philosophy of Frobenius, that when you take a nice function, you write as a linear combination of character, actually you find that in a natural way, it's a linear combination of expression in this quantity called character ratios. So if you want to study the function using this expansion, you want to be able to say something about character ratios, to estimate them, understand how maybe they cancel each other, things like this. So those are representation theoretic objects, and by far the most popular way that people organize representation, build representation, is using Harishandra philosophy of class form, where you build the representation actually by using most of the representation called cuspidals, and they are also, not only many of them, they are very large. This is a very fruitful approach, led people eventually to classify irreducible of finite group of Lie types, the work of Delin and Lustig, and then the work of Lustig itself. But there is another approach initiated by Roger in '73, while you study all irreducible representation in the case of classical groups by very few representation, using very few representation that I will call oscillators this lecture, and I will tell you all about this in the case of SLD. So I want to to work with an example, so I will work with, so you can in some sense judge some choices that we are doing in this theory. So I'll study this problem of a commutator map on our group SL2FQ. So for every two element X and Y in the group, you can build the commutator. And not long ago, I think in 2010, Tiap is here, so Tiap and Shalev and Larsen and Lipak and I think maybe Guralnik also, don't remember. They proved that if you take any finite simple group, this map is this commutator map is in fact onto. And then Shalev wrote a paper, a survey paper, and if I'm not mistaken, he made a conjecture there, or at least he explains that, or at least he gave the feeling that this map is not just onto a finite simple group, it should be uniform. So I want to formulate this. And SL2 is not really simple, but almost. So I need to move away. All the time I will move away from the center of SL2, which is plus minus 1. So let me write this notation for the fiber over G of the commutator map, all the pairs XY that produce this element G, and count the number of elements. This is a map from G times G to G. So it's natural to divide it by the number of elements in G. And then let's say pretend I'm doing now research, so I do numerics, and I go over the conjugacy classes of SL2FQ outside the center. So the elements look like you have non-generic elements of the form plus minus 1 on the diagonal, and then here 1 or a non-square. You have those guys which are diagonalizable over FQ, and you have the guys which are not diagonalizable over FQ but over quadratic extension, or they solve the equation a square minus epsilon b square, where epsilon is this non-square, equal 1. Now you do numerics and you see that as Q goes to be, Q is large, start to be large, don't need to go actually very far with Q and give some concrete bounds. This is 1 plus something of order of 1 over Q. So you can also prove this result, and in some sense I would like to explain a proof of this result. Now, how to
You don't want to exclude the unit element?
Huh?
Because for the unit element, you have about.
Yeah, I take away plus n minus 1. Also, minus 1, it's interesting that you still get a good result there, but anyway, let me not check the center. Yes. So, okay, so I want to, first observation, this is a class function. Extend it as a linear combination of character. In fact, Frobenius proves that it's exactly equal to the sum of those character ratios. Looking to see this result that the numerics showed us, I want to split it as the trivial representation and the sum over all non-trivial representation. There is a spectral gap there. The next level, the next size of representation term dimension already depends on Q. They're much larger. And if you look, you think like this, then it's clear that what you want to do is to prove that this sum of all non-trivial character ratios sum up to something of the order of magnitude 1 over Q. Okay, first approach, maybe every term is small, and then the entire sum is small. Let's go to, again, numerics, let's call it. You do numerics for individual character ratios. And let me start by saying, so I will explain, I will really construct only reducible representation of SL2 today. But to start, I'll just say that there are Q plus 4 of those. And Q of them, I will call them more generic. Later, I will have more appropriate name for them. They are essentially of dimension Q. This is their name for now. There are four representation, little bit weird representation. They come with dimension, two of them of dimension q plus 1/2 and two of dimension q minus 1/2. Now, if you take those guys of dimension q and you check the character ratio, it's 1/q there, all conjugacy classes. And so there should be cancellation. Now, if you look on this column for the non-generic element, the non-generic conjugacy class, actually those guys, the character ratio on them is much larger. It's an order of magnitude 1/√Q. So you might suspect that if there is cancellation in this sum, I better split it into two. Sum over all those small guys and the rest. And so I want first to give in some sense more appropriate name to those representation and those representation.
But small and large is square root of q and q, or small and large is how do you divide what is large and what is small?
So for now I didn't give yet a definition. So in terms of dimension, it's a little bit look like the same. You can, for now, it's just a phenomenon of the character ratio. Character ratio is much bigger. And okay, so first a little bit. First I want to convince that this approach would work. Okay, I'm sorry, I forgot this slide. So what? What? I don't. Steinberg is Q. So in this talk, yeah, I call it guys of order Q. So yeah. So yeah. So take the first sum and the second sum, and let's look, for example, on this non-generic element. The first sum, guys were actually individually really large, but they cancel each other almost to zero, like 1/Q square, the sum. And this other Q guys on this element is what we expect, 1/Q. And for all other elements, you have this quantity. So this is the most interesting, in fact, case, this non-generic element. Yes. So what I want is to first give a little bit more, in some sense, scientific name for those guys. I say small, not so small. So I'll use this terminology of tensor rank. We call them tensor rank. And so one way to see it is similar to how you give degrees to polynomials. So if you have a finite group, then you can attach to it a ring, a Grothendieck ring or representation ring, just the ring generated over Z by the irreducible of G with operation of addition given by direct sum and multiplication by tensor product. And now I want to give degrees to elements there. And now I'm going to make a choice. It's almost ideological choice. The most important guys will be those four representation of dimension q plus 1/2 and q minus 1/2, two of each. And I'll denote this collection by omega. And now you can start to take tensor product, iterate, taking tensor product of guys like this, tensor product L times, and sum up guys like this. So define the tensor rank filtration. The case piece of it is all the guys which appear up to sum over all those things up to.
What does omega mean in the summation? What is
you take
but here it's a set, and here it's what?
No, it's just a set. I just
What's a set? What's the tensor power of a set?
No, it's not. I just meant it's just an algorithm. You take tensor power of guys like this up to L. Individually and sum up. That's all. Yeah.
You don't tensor two of them?
Huh?
You don't.
No, and tensor two of them.
So I think
And taking the height.
Take everything that generate from them using tensor and direct sum.
Is it equivalent to define omega as the sum of the four oscillator representation?
You can, yes, you
yeah, I
can.
think that's the way to do it.
You can. This is. It's the way I did. Anyway, so then you take you get actually a filtration, trivial representation. Those guys, those four guys, And you don't need to continue forever. Actually, the filtration stabilized to give the entire ring after 2 steps. And I'll call a representation of rank K between 0 to n, if the first occurrence, where it first occurs in this chain. Particularly, if I move to the, to the irreducible representation, I will use this notation. This is the trivial representation, G0 hat, G1 hat. It's all those guys, and G2 hat. It's the rest of the guys. So this is for now just it's a choice to give this grading. Judge me if it gives some result, some interesting result, this way of thinking. So now I want to really to see those guys. So trivial representation I know how to see. So those guys, where they appear, why I think of them as a family. So how to see those guys G1 hat, and Andre Wey gave an answer to this.
Actually crossed them.
This remark you say, every lecture I give on this topic, you say this, okay.
I'll show you now.
Okay, so-
I'll show you. He was computing the action of SO2 theta functions that he makes and stuff.
So you actually use this in, interesting.
And by the way, Springer was his student.
Oh, okay.
And he asked Klosterman, said to Springer, do this for higher, other semi-simple groups. And then Springer said, well, I can't compute it like that. Klosterman's idea was you compute the way you compute.
Okay, so I will acknowledge Wey for this, but okay, I understand that there is history. There are also Segal Shale and other people who notice it, and
Did you assume Q odd?
Q odd all the time in this talk, yeah. Okay, so let me describe this yoga that produced G1 hat. So you start with a symplectic vector space, FQ to the 2n. We will just need n equal 1 and n equal 2 in this talk. It's easy to say the general situation. And it's a vector space come with a symplectic form. To isometry, there is only one such thing. And you can take, for example, a matrix with 1 and minus 1 on the anti-diagonal half ones, half minus ones. This is the symplectic form. And then you build a group, the Heisenberg group. So I think this group somehow was discovered by Heisenberg, and Hermann Weyl gave a formulation for this group. And they wrote it down. So you take the vector space, the symplectic space, time FQ, and write this product, WZ times W prime Z prime is W plus W prime, Z plus Z prime plus half the symplectic form, W prime. This group, because the symplectic form is skew-symmetric, this group is slightly non-commutative, it's a two-step nilpotent group with center, actually all the guys living just on the FQ coordinate. So we just FQ, and we want to understand the irreducible of those first thing. There is a map from Heisenberg to W, and W is a commutative group. You have many irreducible one-dimensional representation. For these talks, we don't care about them. We care about the non-trivial representation not of dimension 1. And they are classified by this theorem. The data you need to classify them is an exponential or additive character on FQ on the center of Heisenberg, just homomorphism to C star. You take a non-trivial guy like this, and then there exists a unique irreducible representation denoted by pi psi of Heisenberg group on a complex vector space characterized by the property that the center that should act by scalar because it commutes with everything in an irreducible representation act by multiplication by this scalar exponent z, psi of z. Now this is a representation as many ways to realize it, and here is a realization of it which carry a lot of intuition because it's spaces that people use in harmonic analysis, in standard harmonic analysis. You take the vector space W, you write it as a product of, it's FQ to the L, so you can take guys which live on just on the first n coordinate, and then guys that lives the second n coordinate, call them X and Y. It's just copies of fq to the n. We take complex valued function on x, and then the x guys act by translations on function here. The y guys, this other part, act by exponential evaluate on the symplectic form, and the center act by what it should act. Particular, this is an example of this irreducible announced in the Stone von Neumann. Its dimension is q to the n. Now come they in my story, and say, okay, but Heisenberg has automorphisms. In particular, it has the symplectic automorphism, SPW, SP2N act on W, so it's act on Heisenberg's Swiss action just on the first coordinate. This is an action by group automorphism. So if you fix a representation, this one announced in the Stone von Neumann theorem, and take an element in SP, you can twist it by this element, namely first apply the automorphism and then the representation. We didn't touch the center by Stone von Neumann, they are isomorphic. We know that so if we don't impose more structure, there is this intertwiner is canonical up to the scalar. But it turns out that there exists a unique choice. I think for this uniqueness, you need q is not 3. So let's go above 3. So there exists unique choice of operator omega psi g that realized this relation and act using a product formula, namely homomorphism, acting on this Heisenberg space. Now, this construction depends. I started it as if it depends on the character on the center of the Heisenberg, but the dependence is really tiny. So, in fact, there are two oscillator representation, wave representation. Roger called them oscillator representation. Omega psi is isomorphic to omega psi prime, if and only if psi prime is a twist of psi by a square. So you put a square in the exponent, and you call it psi prime. You do the same yoga, you get an isomorphic representation. So if you take a non-square, you get guy that are not isomorphic. So you have two guys like this, each is of dimension q to the n. Now, this representation is very important for our story, but it's not, and so it's not irreducible. Nobody says that the irreducible representation are the most important. And it's easy to see its decomposition into actually two irreducibles. The center of the symplectic group is plus minus 1. It acts on omega psi. And for example, in the model that we realized it as function on fq to the n, you just send the function f of x to essentially f of minus x, and then the decomposition is just in this. If you think in this way, just the composition into odd and even function. So one space of dimension q to the n plus 1 over 2, and one of dimension q to the n minus 1 over 2. If you specialize to the case n equal 1. Then SP2N FQ, this our symplectic group is just SL2 FQ. And now let me denote the two oscillator representation by omega plus and omega minus, and then further the decomposition into irreducible by omega plus plus, omega plus minus, omega minus plus, and omega minus minus. So these are these four representation that I call them small before. So this is this G1 hat. And relevant to the problem of this commutator map, actually the sum of the character of those guys is just one character, the character of the sum of the two oscillator representation. And for this function, there are good formulas. You can just compute everything for this function. This will be important. Okay, these are the guys of rank 1. What about the guys of rank 2? So here starts the work of Roger. The guys of tensor rank 2, how to see them. And this is Roger. this is an example from Roger's theory of dual pairs. And so Roger told me that in 73, I think he was in Bonn, and he tried to understand the irreducible representation of symplectic group, and he computed certain numbers, and Harder told him that those are numbers that has to do with orthogonal group. And this was the beginning of Roger's theory. So let me describe it in the case we need it. So let me denote by U just the plane over FQ times FQ. And we know that there are two Euclidean structure on it, two up to isomorphism, non-degenerate symmetric bilinear forms. One gives a structure of what's called hyperbolic plane to the plane over FQ. The other is the anisotropic plane. And in the case for the hyperbolic plane, I call it U plus, and the other I call U minus, and the associated form I call this parenthesis plus minus. Now, to this data, you can associate the orthogonal group, just orthogonal group of vertible guys that act on U, preserve the form. And now you can do the following. You can take this two-dimensional Euclidean space and tensor it with our two-dimensional symplectic space. You multiply also the form, you get a symplectic space, a four-dimensional symplectic space, take the associated symplectic group, and this is a group that comes with pair of subgroup. O2 is sitting there through its action on U, and SL2 is sitting there through its action on V, and they commute with each other, and in fact, each is a commutant of the other. All the guys that commute with SL2 is those O2 and vice versa. So this situation of two groups in such a relation inside symplectic group, Roger called them dual pair. And now you can do the following. You take this, so I want to build a four-dimensional oscillator representation. I put something on the center of the Heisenberg, and then I build the corresponding symplectic space with the plus or with the minus. Each got its own oscillator representation. So those are the two oscillator representations. And I can restrict the oscillator representation to the product, O2 plus, O2 minus in each case, time SL2. Then it decomposes into direct sum of representation, one of orthogonal group and one of symplectic group. Going to break a little bit the symmetry here. Going to sum up over representation, irreducible representation of orthogonal group.
What's it on the left side? W plus minus, what's in?
This is I have the plane FQ times Q which is hyperbolic or one is a topic.
W
Restricted.
So restricted, I'm sorry.
Okay.
I restrict to this pair and I want to decompose. I'm summing up over irreducible of the orthogonal group. And for each irreducible of the orthogonal group, it's come in terms of product as multiplicity space. It's a representation of SL2, which I'm going to denote by eta of tau. So I want to describe this explicitly, roughly and explicitly. So first, let me tell you what are the irreducibles of orthogonal group. So the orthogonal group, this orthogonal group, there are four one-dimensional representation. A sign representation, just a plus minus one, interesting guy. There are two character, one-dimensional representation, they call lambda mu, and in specific case, lambda plus mu plus and lambda minus mu minus, and you have the trivial representation. And the rest of the guys, they are all, most of the representation, they are all, I just will say now that they're two-dimensional, easy to construct. All those guys explicitly. And now let me explain in this decomposition with what they come. So the sign representation come with the trivial representation. These guys, lambda plus minus, they choose somehow half of the story of the guys of these oscillator things. So lambda plus choose q plus one, and lambda minus q minus 1/2, and the other guys the same way. The one-dimensional representation, choose the representation called Steinberg representation. This is an easy to describe representation. Just take function on line in the plane and take function with sum up to 0. This is called Steinberg representation. And the rest of the representation, they correspond to, I will write some theorems soon, but they correspond to representation that the name of them, yes, I can maybe recognize them through other theories, but the name of them that I want to associate is the name of the representation of the orthogonal group. So I just call them eta of tau. And I want to say why this makes sense. There is some injectivity here. So if you take the irreducible representation of the orthogonal groups, this list that I wrote, and delete the sign character and those, in each case, the lambda plus or minus that appear, or mu plus or minus that appear, and take the other guy, then you get a representation of rank 2. Those guys are different from those small guys. And in fact, this is an injection, and we call this injection the eta correspondence. So there is theta correspondence, but Roger claims that this is a different mechanism, so we want to call it eta correspondence.
Say a word about the local field case where, of course, the theory, Roger, better behaved and what's so different here? Or somebody
What do you want to say?
Roger, you're going to say something?
Well, I was gonna talk about that, a little later.
Okay. So now you can take the union of the two constructions, and you get all this guy G2 hat. In fact, in this case, there is only one guy that appears in both. It's actually the Steinberg representation. In any event, I know now where all those guys that I call rank 2, they appear naturally through this oscillator representation of a SP4 there. In particular, I just look on this decompositions, and the sum of all character, it is just the character of the two oscillator representation of SP4 minus the character of the two oscillator representation of SL2, those guys that and the character, the trivial character. So in particular, you can if you want to compute this sum, I can just need to compute this sum, and we have formula for the character of the oscillator representation of the sum of them, really explicit, and we know everything about this character. So we can sum as a wrap up. We have all the needs to compute. So the commutator map, it's a map from G times G to G. We wrote it in this way with this proper normalization, number of elements on the fiber over G. G is outside the center. We notice it's a class function, write it as a linear combination of irreducible characters. We decide to split this, to study this, separate this sum over the various ranks. And then you can just use the formulas that sum up over all guys of rank 1. It's just this value of this character of the oscillator representation of SL2, divide by, so the dimension is essentially Q over 2. So let me write it like this. And if I'm not precise, I put some little O notation here. Then if the guy was actually the unipotent element, then it's you get really a lot of cancellation, something of order 1 over Q squared. And for the rest of the elements is something of order 1 over Q. And the same you can do for guys of rank 2. You know that they all appear in this oscillator representation of SP4, and we know the restriction, we know how they appear, what are the multiplicities. So if you just read the decomposition that I gave in this table, this amount, so this sum is equal to the character of a oscillator representation of SP4 minus those guys for SL2 minus the trivial representation. There was multiplicities 2 there, so I divide by 2. the dimension of those representation, all of them is essentially Q. So let me just divide by Q. Put little o for my imprecisions. And again, all those characters, those three characters, that's character of the oscillator representation. We can compute everything for them. In particular, you get this cancellation. So this is realize it. So I want to summarize. I spoke about the commutator map. Frobenius suggests to use harmonic analysis, the sum of character ratios. There are cancellation, you view cancellation. You see the order of magnitude of the character ratios, at least in some classes, it proposed to split the sum over all irreducible into two, guys of rank tensor rank 1 and 2. And then we realize them as families, in particular, realize this sum as a character of some well-known representation and just get the result of cancellation. So I want to thank Peter for organizing again this meeting, and for Roger for teaching everybody this theory, and really happy you taught me this kind of things. That's all.
Questions?
You explained this example so well, and concerned with the Ori problem. There's a problem about S squared. Is it called the Thompson problem, I think, here? And if S is the conjugate class, what S squared, what's the conjecture?
The conjecture says that there is one class where the any element in the sequence group is a product of two elements from that class. So it's like C squared is equal to G. Yeah.
Yeah, C squared equals a G, some conjugate class. So I assume it's known for S, so we couldn't think by that
Yeah.
from this in this kind of argument.
Well, I mean, you can do it directly using the Fourier's formula.
But that's not known in general.
Well, now we know it up to a finite number of possibilities. So that's I think that Michael and I just put.
This obviously this technique is quite general.
I didn't say so. These ideas are already used in many places, in particular people in finite group theory, TIAP, and they develop it in many directions. And so, yeah, but I choose to talk about this, just think it's a personal trivial example where honestly you can understand everything you want to say.
For all the groups, what would you like to take as small representative? For symplectic, I understand, but for us.
So it turns out that if you have a classical group, finite classical group, it appears in a dual pair with something else. So GLK appear with some GLN by
Yes.
and an orthogonal with symplectic, backward, and unitary with unitary. Can build such a situation. Did I classify, Roger, everything now?
But what would you call small?
You can take because you can embed them in an oscillator representation. You can just take the restrictions there. Yeah, I'm sorry, I didn't answer yet. You restrict the oscillator representation to this thing. So, for example, GLK, GLN, yeah. For GLN, for example, this will be the permutation representation, actually.
Maybe a question for Roger. So in Arthur's conjectures of management, which later will give examples of, is this classification that you're talking about consistent with that, I mean, I'm sure I've asked this before, but in other words, with small, you've got the size now. Maybe I'll wait till after you. That makes more sense. And then you will also explain the finite versus local. Right.
So before we move to the bigger room and more questions for this talk.
I guess I was wondering, do you have the slide where you have the explicit, what the data correspondence explicitly gives?
Yeah.
Oh,
This one?
this is this one. So I guess I was wondering, so this top formula, so in the case of the split orthogonal group, you also, if you say this.
You have something which is 1 plus Steinberg, and you need to say more, but.
Okay, but this, you can ignore this in the.
Oh, yeah.
characterization. Okay.
Yeah.
Yes, it's the same place, I guess you need the bilinear form, not just the orthogonal group.
What?
I think you need, when you speak of Euclidean plane, you need the bilinear form and not only the orthogonal group. So if you multiply by a non-square, you will change the additive character you want for the simplex.
Yeah, so I fixed it on the, I somehow fixed it on the Heisenberg group and let the orthogonal group to choose from me which oscillator I'm using, yes. Yeah.
More questions? Okay. Let's take Shamgar again.